Okay, hello everybody. My name is Professor Grant Allan. I'm also the Programme Director for the Environmental Science Programme in the school. And today I'm just going to give you a quick taster of what you might study in the Pollution Environmental Processes pathway of the Environmental Science degree. And the topic of the talk is the global budget of methane, which is also a heavy research interest of mine at the moment. I'm particularly interested in trying to calculate emission fluxes of greenhouse gases into the atmosphere and attempt to balance the measurements we make of greenhouse gas concentrations with what we expect to be emitted from other sources. That's the theme of today's talk. So why am I telling you this? Why is it relevant to you? So a lot of what we're going to talk about today is relevant to the type of research project that you might choose in your final year, as I think other people have mentioned, where you can join in with the world-leading research that we're doing. So I have third-year students that use satellite data, measured data around fracking sites or oil rigs in the North Sea, aircraft data that we've measured over the Arctic, for example, to use that data to interpret it for their third-year projects. And students learn about greenhouse gas emissions and budgets in the pollution environmental processes pathway. Okay, so first of all, greenhouse gases, that all comes under the theme of climate change. And climate change and the greenhouse effect is all to do with the Earth's energy budget. So if we've got 100% incoming solar visible radiation mostly, then about 70% of that is reflected or makes its way back out to space, and some of it is trapped in the Earth's atmosphere. So you can see in that diagram there that the greenhouse gases, all of the gases in the atmosphere in fact, absorb about 16% of the total energy that comes from the sun in the atmosphere before it makes its way back out to space. And as I'm sure we all know, the greenhouse gas concentrations are increasing, and they're increasing very fast, and they've been increasing since the start of the Industrial Revolution in around 1750. And the three main greenhouse gases, carbon dioxide, methane, and nitrous oxide, all follow that very steep incline there, and it's accelerating with time, not coming down. And those greenhouse gases trap infrared radiation with different efficiencies. And because the topic of the talk today is about methane, methane is one of the most potent greenhouse gases. Molecule for molecule, it can trap 21 times more infrared radiation than a molecule of carbon dioxide. But luckily, there's about 1,000 times less methane in the atmosphere than there is CO2. But methane is the gas that's rising fastest, percentage-wise, year on year. And we really want to understand in science why that's the case. So all of these gases have different sources and sinks. They have anthropogenic or man-made sources like CO2, we'll have heard of plenty about. But methane is roughly 50-50 balance between natural sources and anthropogenic sources. And I'm going to talk a little bit about that in this presentation. So there's a provocative question there, methane, an unnatural gas. So we often call methane natural gas. It's the gas that we burn at home to cook our food. And it has lots of natural sources as well, like wetlands. You can see some pictures there. There's a picture on the left in the middle that's an Arctic wetland. Methane hydrates on the continental shelves in the high latitudes, bubbling up into the sea, through the seabed and up through the water column and into the atmosphere. And then there's the anthropogenic sources like extraction of fossil fuels, emission of methane from oil and gas facilities, landfill sites you can see in the bottom left, and forest fires, if they're man-made, of course, emit a lot of methane. And our use of agriculture, cows are a very big source of methane gas into the atmosphere. So our consumption of red meat especially has, and that's why you'll hear that's a very big source term in the when we worry about climate change. So what do we know? Well, we have measurements, so we can record the concentration of methane in the Earth's atmosphere. This plot shows the globally average methane concentration over the past 40 years. So from about a concentration of 1550 parts per billion, so 1,550 molecules for every 1 billion molecules in the atmosphere, it's increased from 1550 to about 1850 parts per billion by the modern day. And it's an interesting fact of the science that in around 2000, in the year 2000, the methane concentration started to level off for a period of about 6 years, and scientists lost interest. We thought that methane was no longer a problem, that it had leveled off and wasn't increasing. But then in around 2006, it started to increase rapidly again, and the shape of that curve with the most modern data is taking an even more steeper incline. So the concentration of methane is rising rapidly. And I've circled those two areas because whilst we can measure it, knowing why the concentration is doing what it's doing in the atmosphere is very hard to answer. So we don't have a perfect answer for why methane leveled off in that 6-year period at the start of the noughties and why it's increased very rapidly since 2006. So a lot of scientists around the world are engaged on trying to work out what the sources and sinks are that can explain or balance the budget and explain those measured concentrations. And one of the candidates that I've been doing a lot of research on recently is working out whether fracking is a source of that increase in emissions that we've seen since 2006. So 2006 is the exact time when shale gas extraction in the United States started to accelerate rapidly and increase around the world. And this is a satellite image from a satellite called OMI, which shows an average concentration of methane excess measured over the continental US, averaged over the period 2003 and 2009. And you can see that there's a red patch there in an area of the United States that we call the Four Corners, right in the center of one of the US's largest shale gas plays where shale gas extraction is taking place. And this is really the first measurement-based evidence that fracking is emitting a lot of methane. Now, a lot of that methane they don't want to lose. This is lost profits for shale gas companies. But the well integrity of shale gas sites in the US and the infrastructure, the pipelines that carry that gas to domestic users, they leak. We know they leak quite often, generally small leaks, not hazardous explosive ones. But this is the first satellite measurement that shows that there's clearly methane being emitted from these fracking sites in the US. So what are we doing at Manchester to answer these questions on balancing the global methane budget? So a lot of my work is trying to measure emissions at different spatial scales. So this is a photograph of a drone system that we built. We have the sort of ones you may have at home for doing photography, the rotary UAVs like helicopters, but we also have these free-flying UAVs, a bit like model aircraft. And we hollow out the fuselage of the UAV and put in methane sensors or remote sensing equipment to measure the concentration. So this is a photograph from a landfill site in Ipswich that we, on a campaign that we did in 2014 to measure landfill emissions. And perhaps the more glamorous research that a lot of us at Manchester are involved with in the Atmospheric Science Group is measurements using this thing. This is the Facility for Airborne Atmospheric Measurement. It's a facility that we're really lucky to have in the UK. It's a world-class facility. You can see the photograph of it in the top left. And it's essentially a small passenger aircraft that would have perhaps been used for short-haul flights to Spain. You may well have been on one if you're lucky enough to go on short-haul holidays to Europe. There's a photograph of it there flying very low over the Arctic tundra at just 200 feet above the ground. It's flown by RAF test pilots. And the photograph on the top right shows some of the instrumentation that's carried on board. This is actually a cloud and aerosol sizing spectrometer. But I've put that photograph on there really because the sort of flying that we do very low level over the sea around the UK quite often, fishermen and people on the coast will often call the Coast Guard or 999 saying there's a plane on a bombing run in the UK because they look like missiles hanging down off the wings. So we have to file flight plans and warn the military air traffic controllers of what we're doing in the emergency services so they know to not take those sort of reports seriously. And the photo on the bottom right shows the fuselage, shows the cabin of the aircraft. And you can see there that the cockpit doors open, so the scientists will sit in the front seats and basically tell the pilots where to go within reason. They have the ultimate control, but we guide the sampling that we want to do with the aircraft. And where you might normally see passenger seats there down the aisles, you can see instrumentation instead, and the pipework carrying the air from outside of the aircraft into instruments on board. And you can see the scientists sitting behind the screens there, looking at the data as it comes in to help us guide the type of work that we need to do, the sampling that we need to do. So I'm going to show you some of the results from these aircraft campaigns. This is a flight that we did in 2012 during the London Olympics, north and south of London on a day when the wind was coming from the north towards the south. And what you can see here is carbon monoxide on the x-axis, the altitude that the aircraft was at on the y-axis, and the colour of each data point corresponds to the methane concentration that was measured. So north of London, which is upwind of the city, you can see it's a relatively flat profile there with just a few reds down at the bottom. But as soon as we go downwind of London, south of London, so winds coming from the north, you can see there the shapes change, the colours change. There's a lot more carbon monoxide in the air, and there's a lot more methane in the air as well. And we can use that data to calculate the flux, the kilograms per metre squared per second being emitted from the City of London using modelling tools and methods that we've developed at Manchester to try and close the budget for a city. And that's going to be really useful for validating emissions from cities as part of the Paris Agreement as we go forward. This photograph shows the aircraft flying over the Arctic wetlands. So a lot of people might assume that the Arctic is ice all year round. So this is summer, this is July over the Arctic at around 74 degrees north in northern Sweden. And you can see here that in the summer all of that ice melts and you're left with these quite swampy areas, and those warm swampy areas, it can actually be warmer than Manchester in the Arctic in the summer. It was 21 degrees Celsius on this day. The Arctic is warming faster than the rest of the world actually with climate change. But those lakes that you can see in the photograph, if you were to be on the ground, you can see bubbles of methane coming up through the surface. So these warm anoxic environments allow the microbes called methanogens in the soils and water column there to emit methane gas into the atmosphere. And Arctic wetlands and permafrosts are one of the big sources of methane that we need to calculate to allow proper, good, accurate future climate prediction. Some of the other work we do is to measure emissions from oil rigs, oil and gas facilities in the North Sea. So you can see the coast of East Anglia there and some sampling. Those are the flight tracks around some oil rigs in the North Sea. And this is work that we're doing with the United Nations to quantify the emissions from oil and gas facilities and compare that with what we think the emissions are from reports that the oil and gas companies might provide, and see if what they're reporting as an industry is valid or not. So you can see there blue colours corresponding to low measured methane concentrations, red colours corresponding to very high measured methane concentrations, and you can see the red dots there, the red blobs. Those are individual oil and gas rigs where the concentration of methane around them is very high. So we're currently completing that work with the United Nations for lots of different oil rigs in the North Sea to see if what is being reported is accurate. And one of the most important tools we have to close the global methane budget is not just the measurement of the methane concentration, but actually the measurement of the isotopic fractionation of the carbon in the methane molecule. So carbon consists in nature of carbon-12, carbon-13, and carbon-14. Different sources have a different carbon isotopic signature. So wetlands, landfills, and agriculture, biogenic sources of methane, tend to have a higher carbon-13 content than fossil fuel sources like coal mines, power stations, and oil rigs, where the gas has been underground for many millions of years. So we can use the measurements of carbon isotopes in methane in the atmosphere to tell us about what the likely sources are. And this is a really powerful tool that we have at our disposal that's been around for about 7 years now that we're using to try and close the global methane budget. So to summarize the presentation, methane concentrations are rising fast. The sources of methane to the atmosphere are biogenic, things like cows, wetlands, and landfills, and thermogenic, so those are fossil fuels and geological seeps. In science, we can't precisely balance the current global methane budget, let alone the methane budget in the past, and this makes prediction of the future climate difficult, especially because a lot of the sources, the natural sources of methane in the Earth system, have a feedback loop with temperature. So as the temperature rises, those methanogenic bacteria are more efficient at generating methane. And we can reach these tipping points where if we melt the Arctic permafrost or liberate methane trapped in methane hydrates in the seabed, we can get sudden pulses to the atmosphere and create a runaway greenhouse effect, which is a real worry. So what are the unknowns? Will we pass one of these methane tipping points? There's actually debate going on among scientists at the moment. We think we may have already passed one of these tipping points in 2006 when we saw that increase, and we think that's been driven by tropical wetland emissions as the tropics warm. What will that mean for future climate change, especially when climate change predictions are based on CO2 scenarios and don't really look at the methane scenarios? What is the correct balance of source and sinks? And the crucial question for any environmental scientist, how can we mitigate this? How can we stop these emissions from reaching the atmosphere? Are there technologies we can use? And what can we do to pinpoint policy for the main sources that we want to get rid of? So that's the grand challenge facing all of us as environmental scientists. What will you do to make our future sustainable? And that's the answer we're all trying to come to. Thank you very much, Rian. I'll stop there and take any questions if there are any.